Today, inshallah, we're going to be talking about we're going to see how to train a fully connected neural network. Okay, so the fully connected neural network, if you remember from last time, it's the most basic form of a neural network. It has some applications. It works. The complicated ones that we saw also last time definitely are, yeah, they work better. But at least if you remember from last time, each had its own purposes. So for the purpose of today, we want to train a neural network or an AI agent in general to be able to classify handwritten digits. Okay, so you'll be given one of these digits. Okay, so the AI will be given one of these digits, and it's required for it to test or to tell you what the value is, what the value of this number, of this handwritten digit. And we're going to do it in a supervised learning way. So if it's a supervised learning, what else do we need to provide? What else? What kind of data? The labels, exactly. So you need to specify. So you need to you need to have a data set where you have these handwritten images. And not only that, you need to also specify that this image is an image of a 3. This image is an image of a 4, 5, 6, and so on. So you need to provide these data. The production of data sets, or the development of data sets, is a big part of AI. If you remember last time what we discussed about ImageNet, what we discussed about, I think it was the deep reinforcement learning, right? The data is extremely important. You already know that from your previous courses. These data sets, a lot of them are already available. Okay, you can just download them. Some are free, many are free, some are for money. Okay, but this is a big part of the AI realm, is that to produce data and to have it available so that everyone can make use of it, and then everyone can already choose his own model to train on and produce an AI program. Okay, but the data itself is a big part. This data set is a very famous one. You can consider it to be the hello world of machine learning or deep learning in general. It's called the MNIST dataset. Okay, it's called the MNIST dataset. So this is what you see here in the title, MNIST. Okay. Are we going to run or are we going to develop the AI from scratch ourselves? I hope we had the time, but yeah, you need to do that in a class solely on deep learning. We don't have time to do that, otherwise we'll not be able to do other stuff. In practice, people don't implement neural networks from scratch. You can do it, like you can have functions, and these functions are connected to each other. If you remember from last time, it's not a neural network is nothing else than a linear parameter, a linear model, right? So a matrix multiplied by the inputs plus a bias. You have some activation function, some nonlinear function. All of these are mathematically implementable, so it's not that difficult. But it's just, yeah, at least once in your lifetime you need to go through the process of doing it. But in practice, you never do it. Okay. One of the most famous packages for that already implement that is TensorFlow. Who has heard about TensorFlow before? Heard about it? Have you used it before? You've used it before.
Yeah, we don't know.
So it's just working. Okay, that's good. So TensorFlow is there's an alternative to TensorFlow that's also famous. Does anyone know it? For Python, it's called PyTorch. Okay, so there's an alternative to TensorFlow. It's called PyTorch. Both are one of the top learning frameworks. There are also emerging frameworks at the moment. Big companies are working on. So TensorFlow is developed by Google. I think PyTorch is developed by Facebook. I'm not 100% sure. There's also a framework by Microsoft and so on. But all of these are considered to be back-end in the sense that they provide a lot of functionalities, and you need to dive into to use their APIs. For beginners, or at least for non-expert users or intermediate users, there are some libraries or packages that are emerging so that you can have a high-level interaction with TensorFlow and PyTorch and so on. One of them is Keras. So Keras is one of the best, one of the available frameworks, right, or packages that you can use, and it gives you a little bit of a higher API. So you don't need to really dive into deep as much as TensorFlow. TensorFlow is much more powerful because it gives you a lot of functionality. But again, as a beginner, you need to learn a lot. So the learning curve is deep, is steep in that sense. Okay, Keras gives you already a lot of APIs that you can use, and they're very similar to this, to the way that people are taught about machine learning. Okay.
So it's
Libraries, both are libraries, right? An API, okay, is a set of functions. A set of functions that you can use, and you can immediately. The data is already in Keras. Okay, the MNIST dataset. So the Keras, if you see here, so this is our first part of the code. So let me run it here until we discuss. So NumPy, you've seen NumPy before. Matplotlib, right? Is for plotting. These are some stuff that we're going to be using. This is the TensorFlow. Okay, so we're going to be using TensorFlow as TF. So whenever the TF is an alias for the TensorFlow, and this is the part that that's related to Keras. So you see, we're going to be importing the MNIST dataset from the Keras.datasets. It's already there. You just import it.
So why import both TensorFlow and Keras?
Because TensorFlow and Keras are two different things. You can import TensorFlow and use TensorFlow as is, use the APIs and the functions of TensorFlow, but Keras gives you a higher set of abstraction. Okay, so something that's more easier to use for a beginner. That's why, but not even just as a beginner, even as an expert that you already know. You don't want to reuse and rebuild the same low-level functionalities of TensorFlow. That's the idea, right? And even TensorFlow is built on even a much like a number of other packages. Keras, exactly. Keras can work with TensorFlow, and it can also work with PyTorch, by the way. So it's a higher set of APIs that you can use with lower backends. It's similar to having a front end and a back end, right? You can have the same front end but different backends. That's the idea. Okay, so Keras is the front end in this case. So you also have the models. The models is it also has like the convolutional model. The sequential model here is the one that we're going to have a number of layers next to each other, which is what makes a fully connected network. We're going to be seeing it later. It has also a number of optimizers. So these are the optimization algorithms that you can use to train. We're going to be seeing that. It has a different number of layers. So that input layer, the dense here, we're going to be seeing is the fully connected layer, right? When you have just a stack of neurals. You have the dropout and activation function. So all of these are already implemented, and it has also some utility functions that will be useful for data. So now we've already implemented all of that. We've run it. You can check whether the TensorFlow is properly installed or not. And yeah, something I forgot to mention is that a nice thing about Google Colab is that it immediately has TensorFlow and Keras installed. So we did not include here in installation. If you're doing this on your own local machine, you have to install first Keras and TensorFlow and Python and so on. Okay. But here everything is already implemented for us. You also know about Google Colab that it already provides you with free computing resources, right? So here, if you check here in this part, we're using, it already has the Python 3 environment set for us, and it already provides us some CPUs and even GPUs for us to play with. These are for free, just with your Google account, and I think you've already had that. Again, of course, these are old machines, very simple GPUs, right? The more fancy ones are, of course, yeah, you have to pay for them. That makes sense, okay? So they give you premium GPUs for money. So if you really want to do something, some heavy learning, you definitely need the GPUs, and we're gonna see this later. That's for we won't even use it today. I think next class, inshallah, we're gonna discuss it. Okay. Okay, so the first thing we're going to do is we're going to be loading the training dataset. Okay, so the dataset is already, you just mnist.load data. It already gives you some of the data for training and some of the data for the test. Okay, the MNIST dataset, it has 70,000 pictures, okay, 70,000 handwritten digits. Each of them is 28 by 28 pixels. Okay, and you see here we're going to print, and it already even without you specifying anything using the default parameters, it will give you 60,000 images for the training and 10,000 for the test. Okay, so immediately you can use it. And if you check here, if we print here the what's inside of the X train and the Y train and the X test and the Y train and the Y test, you see we have a tensor that's 60,000 by 28 by 28. Okay, so it's 60,000 images. Each image is 28 by 28 pixels. We have here 10,000 images. We have here 60,000 vector and now 10,000 vector. What is the Y train and the Y test? The labels, exactly. So it's just either, it's a number, right? So if we print here any of the Y train or the Y test, so let's try it, for example. So let's do a print of Y test of, I don't know, 0. So the first image, you see, we get 7. So this first image, right, in the dataset, in the testing dataset, belongs to the class of 7.
Y train, just number, not image, right?
The Y are just numbers. It's a vector, exactly. It's not images. If you check here.
Can we print Alex?
Yes, we're gonna do that.
What about
Next.
6,000? 60,000.
The 60,000 and the 10,000 is the amount of images or labels in the data set, in this vector, okay?
So we can have 7, for example, repeated several times.
Absolutely, absolutely. Yeah, of course. We're gonna have many 7. Of course, we're gonna be seeing it. So for example, you're gonna have a 7 that's written like this. You're gonna have a 7 that looks like this. You're gonna have a 7 that looks like this or this. All of these belong to the class 7. All of these have a label of 7, but they're different images. Okay. We're gonna look at, we're gonna actually print immediately now some of them. So let's see here. So now we're gonna choose a random 9 images and just print them, right? These are just random ones, okay? 9 images chosen randomly from the training dataset. So if you see here, we look at the training dataset, right? And we do the plot.image show. This is what you use to print images, and you give it like you choose one of these, a random one from the training images dataset, right? We choose that the CMAP. The CMAP is the color map. We choose it to be a grayscale. You know that images can be either grayscale or RGB, right? And there are other ones. Okay, if you have a grayscale image, it has a value from what to what? Each pixel. 255. Well, from 0 to 255, right? If you have a 3 image, then you have the same, one for the R channel, one for the G channel, one for the B channel. This makes it the RGB images. Okay, the MNIST dataset is black and white, right? So it's a grayscale. So it has images from all of the CMAP is a grayscale map. Okay.
So if you have RGB, it will be
It's not you don't, for RGB you don't have the 3 channels, so it's a grayscale image. You cannot, even if you show it as an RGB image, yeah.
this image still on the white as its picture or as vector.
That's a very good point. What do you think? If you look at here, what is the X train? So each one of these 60,000 is what? Is a 28 by 28 matrix. Each matrix has a value of that takes from 0 to 25, and we're going to show you right now.
So here we can print the matrix to see it.
Here you print the images. So image show, okay, takes these pixels and transform it into something that you can look as a picture. If you really want to see what's going on in the matrix itself, which is what we have here. So this is just a funny like a function so that you can look at the details. Is not important what's inside of here, but what it does is simply this. Okay. Does anyone guess what this is?
9.
Exactly, it's a 9. This is it. What this function does is that it will take this last one here, okay, and it will show you what the numbers are. So this is what the computer sees, okay, and this is what you see. This is what you understand as a human. This is what the computer understands.
This is the training state, right?
This is the data stage. So we're still talking about the data. No training, no models, nothing.
Not really yet.
No, there's even no, we're not talking about a model now.
The results, classify 3 to be
That's a very good point. Can anyone answer that question? What is this title on the top?
This is the one.
The labels, the ground truth labels that comes with the data.
Okay.
You need to have that, otherwise you cannot do supervised learning. This is a big thing. Okay, no data, no supervised learning. Go to check to the unsupervised learning. Exactly. So if someone tells you I have the best AI model that can do supervised learning and I can make it work, you tell me and you tell him, okay, sorry, I don't have data labels. Sorry, and you tell you, no problem. Give me money, I'll make it work. He's lying. If you don't have the labels, you cannot make a supervised learning. Okay. So this is, so far we're talking about the data. That's it. So this is how the MNIST data looks like. These are, every image looks something like this.
How do you go this?
Very sim. how do we, so the question was, how do we import these data from here? First of all, we imported the MNIST dataset. If you go back here, you see inside of Keras, the dataset, it had the MNIST dataset. So we imported it first, and then we loaded the data inside of these, inside of a training images. These are training labels. These are the test images, and these are the test labels.
Actually, now when you import the chaos, it's you put a comment about how.
Sorry?
You put a comment before importing chaos.
This one. Oh, no, sorry. This is actually nothing. Okay. I was probably playing around with something.
So how chaos is imported?
Because it's already included in the TensorFlow. Okay.
So we don't need to import.
Yeah, I think so. That's a good point. I think it's already included, but you see from what you see here, there's no error, right?
But there is lines.
The lines, this is a warning. I think it's giving it because probably again, okay, that's a good question because it brings to another point, which is if you look on any of the if you look on tutorials on the internet for Keras or TensorFlow and so on, make sure to always check which version they're talking about, okay? Because these packages, they're always in constant change. So and sometimes the change when they for example do an upgrade, they allow you to use the old notation, right? But and give you a warning until at some point they tell you, and they start giving you a warning that, for example, this is being depreciated, use it in this other way, and at some point it will give an error, right? After some more advancement, tell you, okay, sorry, stop using this way. We're doing it this way now. So this is one of the things that I might have been using like an old way to import the MNIST, but it's allowing it with a warning. That's the idea. Okay.
Also, we can import the Keras without TensorFlow.
Yes, of course. You can, of course. Okay. Again, this is another point. For simplicity of the presentation right now, I'm doing an import of the MNIST and the sequential and so on and so forth, right? All of these. And then inside of the code, I can immediately say MNIST.load data and so on. So it's already imported. A very good practice is that not to do any imports, right? And to always specify, for example, that I have here keras.datasets.mnist.load data. Okay, this is a very good practice. Does anyone know why? Yeah. No.
We don't rewrite on the data.
No. So that from an understanding perspective, you always know when looking at this code snippet, where does this function belong, right? You don't need to go back to the beginning of the code. Of course, now we're talking here about one code, but if you have a huge library, right, different packages talking to each other, different files, you might think that you might have different functions with the same name, right? And you don't know which one that you're using at this point. This is one of the things that can happen. Okay, but now for this purposes, this is okay. It will look, of course, not as nice as this, but it will prevent huge mistakes that could take you weeks of debugging. That's the point. Okay. So now we're printing. Now we're talking. Now let's look at the data. Sorry, let's look at the network. Okay. The first thing that we're going to do is that we're not going to be working with as the input layer. You remember the input layer is okay. Well, let me actually show you this first. So this is the kind of network that we're going to be building. Okay. So we want to take the images, okay, that we have, give it to two-layer network, okay, only one hidden layer and one output layer, and then it tells us what this image is. Okay, the way it will be doing it, the first thing that we need to do is that we need to specify here, okay, we need to change the 28 by 28 pixels into a vector that's 1 by 784. 784 is equal to 28 times 28. Okay, this is called a flatten operation. Okay, this is just it's like a pre-processing. You can even do it inside of the Keras allows you to do it inside of the network, but we're going to be doing it before by hand. Okay, so that's the first thing we're going to do. The second thing, you remember what was the label? It was one number, but here we have 10. Okay, so what we want the outputs to be, we want to have 10 outputs. Each one of these corresponds to one of the labels. Okay, and the network that we're going to developing will not give us a number in the end. It will give us 10 numbers. Each represents its confidence in the which class this picture belongs to. So it will give us a probability distribution, okay, in that sense. Okay, so this will be the output.
So you have 10 different ones.
You're gonna have 10, you're not gonna have one number that tells you this picture is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You're gonna have 10 numbers, each between 0 and 1. It will tell you, I have 10% confidence that this picture is a 0, 20% confidence this picture is a 1, and so on.
Like the example you gave us, for the zero line, the picture that conventional layer example.
Yeah, yeah.
0.7.
Exactly, yes, exactly. It's exactly this. And of course, the probability of these numbers, they have to add to what? To 1, exactly. So all of the numbers that will be inside of these 10, inside of this layer, they have to add to 1, okay? So again, all of this can be done inside with Keras. We're going to be doing it just by hand to show you how it, just for simplicity. So what we're going to do here is they're going to be reshaping all of the images. We're going to be reshaping it into a 60,000 vector to a 784. So we're going to be shaping the images to a vector, okay? What we're going to also do, we're going to be changing the integers, okay, to 32 bits, okay, just pre-processing. Another important thing that we're going to be doing, we're not going to make the values of the pixels from 0 to 255. We're going to normalize them to be from 0 to 1. Have you discussed this before in the AI course before? Normalizing the input.
From 0 to 20.
Instead of from 0 to 255, we're going to make it from 0 to 1. Does anyone know why? Okay, let me tell you later, okay? Not now. Okay, just for time's sake, okay? Because it needs some maybe I'll include inshallah in next lecture, okay? But keep it in mind that, okay, this is something that makes a difference in the learning, okay?
Normalize each pixel.
We're going to normalize the value of the pixel. So instead of having a value from 0 to 155, exactly. So this matrix, instead of making from 0 to 255, we're going to be dividing it by 255. So all of the numbers inside of here will be from 0 to 1, right? Again, with the same ratio, okay? But it makes a difference. You can even try it yourself in the, actually, I'm going to post it in the homework, inshallah. You can try it yourself.
Learning be faster or
we need to think about it a little bit more, but for now, let's skip it for time's sake, okay? Here, to change the integers, okay? Because here we had an integer. Okay, first, does anyone know if we divide it by 255 without making the type float 32, what will happen? What?
integer.
We will not have the fractions. You want to have a fraction, you also want to have from 0 to 1, but with fractions in between. If you keep these as integers and divide by 255 and cast it as an integer, you're going to lose all the fractions. That's why we make it a float first. 0 is black. 255 is white. Everything in between is gray with the different levels, okay? This is the color.
Float, so it's float, but 32, what is used for? 32, float 32.
The float is the
To have a
decimal places, exactly.
but 32, what is?
Because you have 32 or 64, you have the precision. You remember that? Does it ring a bell? Right? How many decimal? It's like inside of the computer. What's the biggest number, the smallest number that you can represent with this? Okay,
You mean the letters, right?
what? Exactly. Yes, 32 bits and 64 bits. Exactly. Okay. So now we've reshaped. So now we have, this is the input images. So now we've flattened all of them. Also the outputs, we're going to be formatting them. Instead of from 0, we're going to make them into like all of these 10 numbers. Okay. There's a nice method that does that. It's called 2 categorical, and it's already included in Keras. We're going to be using that. And that's it. So now we have the data ready. Let's now start with the neural network. Okay.
What did you do with that?
The output, I transformed it from, where was it? From, instead of having one number to be 0, I made it 10 numbers, each with that represent the probability. That's the idea. So in the end, if you get if instead of having that one number that tells you a 0, so this represents a class of 0, you're going to have it in this way. If you get here 1 and the rest 0, then the network has 100% confidence that this image corresponds to the 0, and the rest and 0% confidence in the rest of them. These 10. So these are will be probabilities now. This is what I did in the last part. Okay, transforming the output, the labels into this way. So now we have the labels in this way. We have the input images into flattened, and now we can ready to build the network. Okay. The model. Okay, so this sequential. So we're gonna have, if you remember, or also for people who came late, we're gonna have a fully connected network with 2 layers. Okay. When I say 2 layers, we don't count the input layer. So we always have an input layer. So when I say that it's a 2-layer network, this means that it has 1 hidden layer and 1 output layer. Okay. So the sequential. So the first thing is that we're gonna create an empty neural network. So we're gonna use the sequential. So we're telling the network we're gonna add a number of layers sequentially. So this is what we're telling the network, and sequential is included in Keras. First, we're going to add the hidden layer, and we're going to choose it to be a number of n nodes. How do you choose n? So what's the number? Exactly. You choose. Use your network, your call. Okay? You say, I want the n to be 5, 10, 6, 7, whatever. Okay, 100, 500, 1,000, and so on. If you remember from last time, from the universal function approximation theorem, but we have a proof, theoretically, that while n goes to infinity, we can perfectly capture the map that goes from the images to the labels. Okay, we can do it, but of course, n of a million is maybe too complicated. This is why we divide it and make layers and so on. Okay, we're going to be choosing. So first of all, we added the input layer. This is how you add it. You say model that add input, and the shape is 784 by 1. You add a dense layer, and you add an activation, and we make this dense layer have an activation function of Rayleigh. And you can do this. You can do this step and this step in the same line, but this is written for simplicity.
What did you choose?
That's a good point. How do you choose the activation function? Your call. Okay, this is just the example that I have prepared. Do whatever you want.
It will be, if you choose, for example, sigmoid, it will be more complicated, right?
That's the homework. You play around with it. That's precisely the whole idea. You don't know. No one knows. Okay. You can choose activation function, any one of these, and you try. Okay.
So n and the activation function can be anything.
Exactly. We're going to talk about it later. Okay, in the end, inshallah. Okay. So now we have added this part. Okay, let me check. I'm going to run this part again. Okay, I'm gonna add, and then I'm gonna add the output layer to be a dense layer of 10. Okay, and I'm gonna make the last activation function, and this is also important, to be a softmax. Have you seen the softmax before? Ring a bell. In theory,
Yes,
I think so. Okay, what? It will. Yeah, exactly. It has something to relate. It will not take. It's related also to having the maximum, but with some sort of nonlinearity into it. Okay. Okay. Next, go back to your notes. Take a look at it, and I might also include here in the tutorial some picture of the softmax to remind you of it. Okay. The Keras has a nice built-in function to tell you this is the network that you've inputted. This is very important before starting the learning. Okay. Make sure that what you wanted, okay, theoretically on paper is already included in the code. Otherwise, if there is an error and you start the training, you go for a couple of weeks and come back, you've wasted a lot of time. Okay, so this is the kind of network that we have. First, it had, again, the input layer, no one talks about it. So it has the input layer, of course. And then we have one layer that's dense, okay, of the shape of 128, a vector. We have an activation function, okay, that's it's not mentioned here. I think so. No, it's not mentioned. Okay, we have 128 activation functions, each for each node, one for each node. This is the same activation function, activation number 3. We have another dense layer 4, and we have its own activation 4. Okay.
What is 128?
128 represents the number of neurons we chose to be in this hidden layer. Okay. And the output layer has to be 10. Why? The number of layers, exactly, because you have 10 classes. This is a classification problem. This is a multi-class classification problem. So you want to classify the digits into 10. So you need to have in the end 10. What's in between, right? It's up to you.
And in these last, we have, for example, 1 0 0 0 0.
We're gonna see that. Wait, okay. You're gonna see immediately what's gonna happen, inshallah. And that's it. Okay, so this is the model that we have. I have a question for you. What is this part? Okay, what is this? Exactly. The number of parameters. You remember the theta? What was in the theta? The bias and the all of the parameters inside of the weight matrix. Okay. How do we calculate this number? That's the question. Then this is 100,000 for 180 number of parameters in this simple network. You see, we have only 128 neurons. Okay, and we have here 100,000. Okay, the number of parameters, okay, in neural networks might be millions, billions, and even. Okay, this is completely normal. Okay, so this is 100,000. So this is a baby network in this sense.
So this is the matrix inside each.
Yeah. So first of all, if you remember here, so if you remember from last time, we had inside of here the weights. How many of these? It was a matrix of size 784 multiplied by 128, so the n. And how many biases did you have?
For each,
The biases had the same length as what? Nope, as the previous one, right? Take a look at the last lecture. So the number of weights in this part of the network is 784 times 128 plus 784. Check that out. It will be 10,480. The number of weights in this part of the network is 128 times multiplied by 10 plus, are you sure? Plus 128. Okay. Here. So 120, sorry. Okay, no, sorry. No. No, sorry. The number of the bias has the same number as the current layer. So here we're in the first layer. Okay, if you remember from last time. So we're talking about this first layer. So the number of neurons inside of here is 784 times 128 plus 128. The number of outputs, the number of weights in here is 128 times 10 plus 10.
plus 10, this is for the bias, right?
The bias, exactly. The bias is related to this vector, okay? Not to the previous one, and so on.
But we have 128 more, so it should be plus 128 more.
No, the 128 is the previous. If you go back to the previous last lecture, you had the weight of the ith layer multiplied by the y of the ith layer plus the biases of.
Because the addition should be have the same one.
It's a good. Yes, that's right. Yes, right. That's why. Okay, let me rephrase it. Actually, the matrix inside of here will be 128 times 784, because the 784 will be multiplied by the number of inputs, which is 784. You're gonna get an 128 vector. You add the 128 vector. Okay.
So only 128 multiplied 784.
It's 128 exactly to multiply by 700 plus 128. And here the weights inside of here is 10 times 128. You get the input, which is 128. You get 10 in the end. You add then the 10 that's biased. Okay. Go back to the previous lecture. You're going to find this number. Okay. A good practice to test yourself with it once in a time. Now we have the model. Okay. And now you need to say this is a network. That's it. Okay. What is the number that you chose for the weights? How do we choose them? This is the whole training process, right? What is the weights that now you have the number of weights, but what are the weights themselves? What is the matrix W of the first layer? What's the weight matrix W of the second layer? What is the bias of the first layer? What's the bias of the second layer? All of these numbers. Okay, now we're going to optimize for. We're going to do a search. We're going to do an optimization. This is the training process to try to find these. Again, everything is implemented in Keras. We just need to know how to use it. You need to provide some stuff. You need to tell it which loss function you're going to be using. remember from last time. You need to tell it, oops, sorry. You need to tell it which optimization function you want to use. It has a huge number of optimization functions that are implemented. And you need to tell it if you wanted to calculate for you some metrics that are happening inside of this training process so that you can look at it later. Okay, and a lot of stuff are already built in. If it requires special metrics that you need to look at, you need to implement some of the codes yourself. That for next time. I'm going to show you something next time, inshallah. Okay, that's not built in, and how can we call it? Okay, wait for next time, inshallah. If you remember, you've probably seen this before. We did not discuss it last time, but you've definitely seen it, right? Which is the way we do this process is using the gradient descent, right? And we need to calculate the gradient, so we use the Bragg propagation for that, right? This to do the Bragg propagation, then we depend on the whole training set, and this is too expensive, right? So what do? We use stochastic gradient descent, and we divide the training set into mini batches. Have you seen this before? Right? Does it ring a bell? Having the batches, right? Okay, I'll say. Have you seen the word epoch before? Epoch? No. Okay. What? So this process that I just explained. Okay, so we take the whole data set and we divide it into batches. Okay. Before doing that, let's do something first. Here, this is the number. We're going to be choosing two algorithms that we're going to be playing around today. Okay, the stochastic gradient descent and another algorithm called Adam. Okay, you've probably seen, I think, before the stochastic gradient descent, right? How it works and mathematically how does it work? Right? Have you seen that?
Choose a random point and start the gradient descent algorithm and a function.
It's not 100% that. The stochastic gradient descent is also related to the batching. This idea that you divide, instead of looking at the whole data set and calculating the gradient, we approximate the gradient by dividing the whole data set into smaller batches, and then we calculate the parameters for this one, and then update for the next batch and so on. So we do it for batches. Okay, and after we do that, we've run the whole the parameter update on all of the batches. This is called one epoch, because just terminology. Okay, so if you have done two epochs, how many times have you calculated the parameters over the whole data set? 2 times. No, 2 times. The one epoch means that you've taken all of the images of the training data set, and you've already calculated the gradient based on these. That's the idea. Okay.
First you divide.
But the division itself is up to you. You choose how many batches that you want to have, and I'm going to show you right now. But what we're going to be doing here is that let's try first the stochastic gradient descent. And if you remember from previous course that in the gradient descent, right, you need to specify the learning rate, right, the learning parameter. It was a number, right, from 0 to 1, I think, right, and then you need to specify it so that you know how fast. Oh, sorry, it's not from 0 to 1. It has to be greater than 0, and you need to specify so that you know how many, like when moving in the parameter space, do you take large steps or do you take small steps in the parameter space? Okay, so this is the number that you choose. Again, a parameter that you need to play around with and define. We're going to choose the default one inside of the SGD constructor, which is 0.01. I know we're going to play around with it later. Okay, and here, which shows that we want to have the loss function, something that's already implemented. It's called the categorical cross entropy. Right, I'll tell you about it, the details later, inshallah, if we have time. And then we choose that the optimizer is our optimizer, so the one that we defined here. And we say that we want the Keras to track the accuracy for us. Okay, and it will keep track of the accuracy. The accuracy is what? How do you calculate the accuracy? Exactly. You also give it the labels, right? So accuracy of 1, what does it mean? 100%, right? If you give it an image, it gets the label 100% accurate. That's the accuracy. Okay. Okay.
So
now
you choose the optimization function and the loss function.
Yes, exactly. You choose the SGD is the optimizer, stochastic gradient descent, and the loss function is the categorical cross entropy. Okay. As far as I understood, from the only loss function that you saw it and play around with in the previous course was the least square error, right? Okay. So again, different loss functions for different problems. Okay. the mathematics of the optimization is the most important part in the learning, okay, in machine learning and AI in general, and it's the least understood one because it's the most mathematically involved. Okay, so to really understand machine learning or AI, you need to have very, very strong background in optimization, and you can take several courses, not just one. That's why this is the thing that we're gonna never talk about. Okay, it's forbidden in this class. Okay,
The method of optimizing.
the mathematics of the optimization itself. How do you update? How do you go from one parameter to one parameter? What you see here is that it's implemented for you and you get the results. But really to be an expert in this stuff, you need to take a course on optimization, okay? From a mathematical point of view.
So this optimization will be update each way.
Is how do you update? It's the algorithm that you use to move in the parameter space. This is also related, by the way, to the search algorithm that we're going to be talking on, because you have the same problem, by the way. Searching, when you have a search space and you're moving from one point to the other, right? You're using the A star or the blind search, the breadth depth search and the breadth first search or the depth first search and so on. All of these algorithms, they are searching in a space. It's a kind of optimization. Okay, here's the same. Okay. Now we're going to be starting the training here. The training is done with one line. This is it. Okay, you say model.fit. Okay, so we had the model, we created the model. We said how many layers there are, what the type of layers and everything. We said that we had here the model compile. So we compiled the model with its own algorithm that will optimize it. Okay, we chose it. What? It's the name of the function. Compile is the same. It's the same word that we use to compile code, right? You've written the code, but now you want to take all of this information and put it inside of, like, inside of this, it already selects pre-written algorithms, right? That will do the loss function and do the optimization and so on. And now this is the training, that the whole training process. This is the part in the machine learning that takes the longest inside of the code. This is the thing that will take weeks or months, okay, on supercomputers if you have big systems, okay, and big companies, of course, do that. What we need to specify is that because we're using the stochastic gradient descent. We're not using the basic gradient descent, which you can do, of course, and it's implemented. This is the most computationally expensive, right, and definitely not the best. Okay? This is why people are working actively in designing these algorithms. You need to choose the batch size, which is how many images. We're going to define we're going to divide the dataset, the training dataset, into a number of smaller datasets. Okay, so we're going to divide it by, okay, sorry, we're going to have 128 images per this small dataset for the approximation. We're not going to be computing the gradient at once. We're going to be computing the gradient approximately and then adding. This is the stochastic gradient. What? The gradient descent does that, but you need to specify how many images do you want to be in these batches. That's it.
What's the other algorithm that will take it off? Not divide the data.
The gradient descent. Gradient descent takes the whole data set as one. 60,000 images, takes them at once and calculate the gradient of the loss function with respect to the parameters at once. The stochastic gradient descent tells you, okay, I'm going to approximate that gradient, divide it into many batches, right? And then get the parameters from the first batch, then update the parameters with the second batch and so on. After I finish all of these batches, I would have ran over the whole 60,000 images, okay, of the training data set. And this is considered one iteration on the whole data set, right? How many times do you want to repeat this process? So you remember, so it's like we're having an inner loop and an outer loop, okay? So we calculate the gradient with these batch sizes, and after we finish the whole data set, the 60,000 images, we take the parameters and then we run again on the whole 60,000 images. This is the epochs. So how many epochs do you want to run? Okay, that's the idea. So these are the two numbers that you specify. How do you choose them?
Epochs represents each batch or whole after reading all the batches.
After reading the whole batch, all of the batches, this is one epoch. How many times you want to repeat this process of optimization over the same images? This is the number of epochs that you have.
And the result of one epoch will be graded for each batch.
Where the patch is like intermediate steps, right? You're gonna have intermediate steps, but at the end, you only have one set of parameters that were output after the whole training images. Okay, clear?
Every batch will go at 5 times.
The 5 is the outer loop, and the 128 is the inner loop. Okay, so inside of the inner loop, we take 128 images, we do an update of the parameters. The next 128, we get a new number of parameters. You get a new set of parameters, right? Okay, and so on and so forth. And then in the end, you've after finishing the 60,000 images inside of this inner loop, you got one update of the parameter. You repeat the whole thing on the dataset and so on. Okay. Okay, did we run this? Yeah, we did not run this yet. And the rest, what you see inside of here is extra stuff just to calculate how much time this will take. So we record this, the start time, we record the end time, we calculate how much time has elapsed, and we print it. And this is your first neural network trained. Okay. This is where you sit down, go have coffee, come back, sleep, if you can, of course. If your thesis depends on this this algorithm, I don't think you're going to sleep. Okay, we finished the learning. Okay, took 12 seconds. Remember, this is a baby neural network. Okay? This usually takes weeks or months. Okay, what you see here is that the algorithm started with. Okay, what you see here is that we had a number of epochs. Okay, and inside of these epochs, it was doing a number of iterations. So 469 iteration, what was these? What? The number of times you were doing iteration, because you divided the data set on 128, right? Batches. So you had to do all of these inner loop. And so we had an inner loop of 469 and an outer loop of 5. Okay, so this is what this part was doing. Okay. And now, after the first epoch, our loss function had a value of 1.6568, and it had an accuracy of 53.5%. Is this a good network? Very bad, of course. What does this mean? Exactly. You give it 2 images, one will be right, one will be rough. One will be right, one will be sorry, one will be right, one will be wrong. Okay, not right and left. Okay, right and wrong. Okay. Second epoch, much better.
But already in each epoch it's compared with the test, comparing the
with the labels, of course. It's using the test data set. Sorry, it's using the training data set.
Not using test data set.
Very good point. Very good point. When do you use the? Okay, during the training, you should. It's forbidden to make any. It's forbidden to touch the test data set. Forbidden, because if you use any image of that, okay, then you're already validating the network before training it. Okay.
So what this case for?
This is the accuracy of the network trying to predict the correct label that it has, because you give it a label and you give it an image. Okay. So after the first epoch, it calculated the network, the parameters of the network. So when you give it an image, it will tell you, I think this image is a 5 or a 4 or a 3 or a 2. You compare it to the actual label, right? And you see whether it's correct or not. This is the accuracy. And you see with time what happened after the number of epochs, the accuracy was reached what? 90%. Are you satisfied? Okay. If you're good, go move on. That's it. The neural network training done. That's it. Congratulations. I'm not satisfied. Very good. If you increase the number of epochs, what will happen? Who knows?
We can increase the training.
Very good point. Let's try that. Let's play around with the training rate. First of all, this took 12 seconds. Maybe let's see if we can get it faster, right? But do you think we're going to get it faster and the same accuracy? Or we're going to remember, the accuracy means that you've already reached a number of a choice of parameters, right? So in the parameter space, you've run to one point, right? This point, of course, is a huge vector, right? It's the 100,000 vector, but it's one point in the parameter space. So do you think we're going to get the same accuracy? and we're just gonna learn faster, or the learning rate affects also the optimization value that we need in the end, the optimal value of the game. What do you think of the parameters? Let's see.
Victor didn't take the training before this. The first iteration, I mean. Okay.
That's a very good point. That's a very good point.
Start a new training.
Actually, you're actually right. The way I ran it right now, it started with the initial guess of the parameters to be the last one that we reached. And how do we know that? You see here, what was the initial accuracy?
It's the same as
Was the same as the one that we lost. So if in order to do that, to really test it, you need to go back here to the sequential. You need to restart this. Okay. Make the model from the start. So this will delete the one that we had before. Add all of the layers. Look at the summary. Okay, so everything now is clear. So now we're going to be starting from a random point in the parameter space. We'll do the SGD with a different learning rate and start the fitting. You see here? It didn't start from the same point, but it's definitely better from the 50%, right? So what's happened here? Okay, wait a second. There's a disclaimer here. This is the value after the first epoch. It's not the initial value that it started with. If you really want to know what the accuracy of the model before the training, you need to add some code yourself. But here this is after the learning, after epoch 1, exactly. Not before epoch 1. So there's no epoch 0 here. So there's no the value that you started with. So we don't know. But with some extra code you can do. Okay. What? Not necessarily. If you start with a random number of points, a random parameter, it can be very low, but not 0. Okay. So here we get okay. The learning rate didn't differ much in the time, but what did it affect? The accuracy. This means that in the first time we stopped before the optimal point. So the optimal parameter, the optimal point of this optimization problem. And now even we just changed the learning parameter, how much we search this huge parameter space of 100,000, and we reach another point. So you see, even if the same time affects, even if it takes the same real time, right? The learning rate makes you go to a different point. This is the parameter space, remember? We're trying to look for the optimal parameters. This is what we're optimizing for.
So one of these.
Not one of these, all of these. You have an infinite amount, you have an infinite, okay. So for each one of these 100,000, I think it's 101,000, something like that, and some extra stuff. For each one of these parameter set, each value can take a number from negative infinity to infinity.
Okay.
Right? So this is a approximately 100K vector.
So this learning rate will approximate these parameters.
Will send you to a different optimal point. That's the point.
So we'll keep changing this all moment.
Even in the same time. So even if you take less time or more time, you get a different point. You jump to a different optimal point, which in the end is a different behavior of the network. Okay. So by changing, so the bottom line is that if I change only the learning parameter, I might get a completely different model from you. That's the point. And then different performance. Okay. I'm going to choose the Adam function. By the way, the Adam has better performance in this sense. And let's also restart. Let's see. I don't know. Maybe start this one again.
Also, to divide the data batches.
Yes, same. Yeah. Okay, 1, 2, same. Now we're gonna do the Adam.
Can we use different Adam and previous ones, 3 iteration and we done?
You mean what do you mean? You mean
we do three iterations with 3 different ones.
3 different networks
No, the methods Adam and the
combined.
yeah 3 iterations.
For each iteration.
That's a good point. Yeah, of course. Yeah, you can train the first network using SGD. Take the initial guess, that the final result of the parameter that you got as the initial guess of the next one, and move on and so on. Of course you can do that. Yeah.
So why we didn't do it?
Is it guaranteed to give you the best performance? You never know. I might use the SGD for only for 5 iterations, and you might use both for 5 iterations. You get different performance. Try it yourself. Try.
So the learning rate is related only to one migration.
Is related to in every is related to the update between the epochs of the values of the values of the parameters. Okay.
So as we increase the learning rate, it will be better or depends. No one.
Exactly. What's the accuracy we got here? 97%. Let's stop here. Okay, that's good enough. Okay, now let's play around and see. This is the point where you go to the test data. Only here. Only here. You finish the learning. Okay, and it's even a good practice to give the test data to someone you don't know. Okay, after finish the training, call him, tell him, give me now the test data I want to try. Now he gives it to you. Okay, the test data and the test labels. Okay, without the labels, what happens is that you take one of the images in this X test data, you give it to the network. It will tell you what? It will give you 10 numbers, right? What are these 10 numbers? What? The probability of what? Of that image belongs to what? Belonging either to the 0 class, to the 1 class, to the 3 class, and so on. Okay, the evaluate function is already built in Keras. What it will do is that it will do this on all of the algorithm, on all of the tests, all of the images in the test dataset, and it will tell you that in the end, the test accuracy. Okay, so the previous number, this number, was the accuracy on the training dataset. This is the accuracy on the test dataset. It's very high, which is very good. Okay, if you tried and try this at home. If you try to do more and more better accuracy on the training dataset, is it guaranteed that the test dataset will work? Sometimes you can get very good training dataset, training accuracy, and very bad test accuracy. Why? What is this problem called? Overfitting, exactly. You've trained the parameters very well to identify the images in the test dataset that becomes very hard to generalize. Okay. Now we've left some error. So it's not 100% accuracy on the test dataset, sorry, on the training dataset, which give it a better chance of generalizing. Okay. And now this is a very good generalization because the images in the test dataset, the network has never seen before. Now let's play around with the now let's look at what happens. So now the training is finished, the model is done. Start your business, deploy this model, and get a lot of money if you can. Okay, that's it. Now let's investigate a little bit more. What's going on really? Let's see what the images are producing. So the model.predict, if you give it that X test, it will calculate the probabilities now to calculate the outputs. Okay, in the first one, it already evaluated and tested with the test labels. But now let's look at the probabilities. So now we finished, and now we're going to do some post processing. All of this is post processing. What? Predicts it gives you so if you look at any of these probabilities, let's do that actually. So let's print the probabilities dot shape. Okay, what do you expect this to be? The shape of this probabilities variable.
10.
It's 10,000 by 10. It's the 10,000 labels, but each table is not one number. It's what? It's 10 probabilities. Exactly. Okay. How do we say that? How do we make the network choose in the end the label of this image? We do what? We take the maximum. Exactly. This is what happens here. We take the arg maximum of the probabilities. You see which one is the maximum, and you say the network will tell, if it tells you, I think you're Khalid and you're Muhammad, then it's already decided. But in its working, it has a probability that you're 60% Khalid and 50% Muhammad. But in the end, I chose the highest.
5,000 of these 10,000. For example, 1000, then it will decide if it's number 1.
Yes, exactly. Like number 0. The 0 is the first number. Exactly. We're going to see also this. Now let's plot the images. The details of this, you can look at it later. But what we're going to be plotting here is this. we're going to choose a number of the images that it predicted correctly and the number of images that it predicted wrong, and see if the network is really has an intelligence. Now, this is the point where you use your mind to see whether actually the network is an intelligent agent or not. Let's see here. So when I drew this image, I drew this digit by hand. It said that this it predicted to be 7, and it really was correctly 7. So it belongs to the class of 7. This was a 2, 1, 0, 4, 1, 4, 9, 9. Now let's see what's going on here and the things that it got wrong. Okay. What is this number? It predicted to be a 6, but what is it really? Okay. Do you think the network did a good job here or not?
Yes.
Yeah. If it was me, if any one of you in the exam writes a 6, a 5 like this, I'll say it's a 6. What about this one?
It's too clear.
Is it clear too? I know people write 7 like this. Sure, maybe French and you have like a little bit of an extension. What about this one? Maybe it was a 0, but it's in a hurry, right? It also works as a 0, right? What about this one? Come on. You remember last time what we mentioned about the features. What's going on in the hidden layers is that the network divided the images into a number of features. So it said that this is a 3 because it has most of the parts of what the 3 has, except for the last part, right? But it said, okay, yeah, it's almost a 3. The 5 would have something here, a feature that goes that you write it this way, but the 3 has a feature that goes the other way, and the feature was not there, so it predicted to be a 3. What you can actually do is that let's look at really the probabilities of what the network thinks of these numbers. So this is after the softmax, sorry, after the argmax, after you've decided the image. But here, if you look at, for example, let's take this picture. It said it was a label of a 6, but it had 35% that the image was 0, 1, 2, 3, 4, 5. It has a 35% that image was a 5, and a 52% the image was 6. So choose the 6. So you see, it does has intelligence. It does think it's a 5, but it's more likely it's a 6. That's why it says it's a 6. This exactly. This is the output of the output there, absolutely. And this is what you show to the user. The user does not want to see all of that, or sometimes it does. Sometimes it might be helpful that you put some probability here. Okay, and this is all. Yeah.
For example, so it's predict 6, but say maybe.
Or say that it predicts it's a 6, but it has a 52% chance that it's a 6. It's not that high, right? The last 2 ones. Okay, so this one predicted to be an 8, but it was a 9. Okay, and it did a very good job, right? Because if this was an 8, it would have missed this small feature. Let's actually go to it. So this is the last 2 pictures. This one. So this is the 8 and the 9. It has a 60% chance it's an 8 and a 30% chance it's a 9.
It has all the features that it's
That's right.
so one
Because it's not it does mistakes. So it has intelligence. That's for sure. But it's not as intelligent as you would get it, right? That's the point. So that's the point. Intelligence has many layers, right? You can be smart, you can be a genius. Both are intelligent. That's the idea. There's a question here.
Also the 8.
What?
The last one.
The last one, this is definitely wrong, right? This is stupid. Okay. Again, maybe it was had some caffeine and it was not sleeping well and so on. What?
Can you show the probability?
The probability of this one. You check here. It had a 47 probability it was an 8. Sorry, it was a 2. But also a 31% it was an 8. So it is a little bit, yeah, maybe with some tweaking, right? It can get it better. But again, getting it wrong is built, it's already an integral part of it. A neural network will definitely get some stuff wrong. Okay.
If we flip the picture, will it be catch it or?
Very good point. Try it yourself. Very good point. I don't know. take the test data. That's a very good exercise. Maybe I'll make it in the homework. Take the images and do a rotation for it and see what happens. That's a good point. Good exercise.
So we don't know how to rotate this.
I will rotate it for you. I'll give you the test data. You do it. Or maybe I'll put it as a bonus. Okay. Last thing I want to show you is this. Okay. When you're watching the training, okay, these are the two curves that you keep on watching. Okay. Every epoch, you're gonna get a new value here for the accuracy and a new value for the model loss. Okay. If the model is losing, if this function is going down and down and down and down and down, what are you doing? You're learning, and it's getting better and better and better and better. Okay, that's it. Okay, there are some advanced stuff that I want to talk about, but good that the time is done for now. And this is related to next time, inshallah. So next time we're going to look at some more advanced stuff that you can do for the training to understand the training, what's going on. So this is more of an advanced way to debug the network. Now it's working. Now, congratulations. This is your first neural network and it's working. Has 79% accuracy. Very congratulations. But maybe on more complicated examples, things get more nasty next time, inshallah. And also we're going to be talking about the neural network, the convolutional neural networks next time. And this is the thing that you were asking about. These are called hyperparameters. They're all of these parameters we made a choice on, and we got this result. Can you change it? Of course. Change the number of hidden layers. Change the number of nodes and the activation functions used per layer. The solver parameters, the learning rate, the batch size, the number of iterations, how many epochs do you choose? Here we did only 5. Your question is, if we made it 10, is it better or not? Try it yourself and see. And there are more stuff related to optimization called the regularization, but this is for later, inshallah. Okay.